All right, well, I thought it would be, given that you have to program against an interface in the coursework, so you have this notion of a ring that you use to give the semantics to polynomial, I thought it would be appropriate to show you how we do that in ACTA with a simpler example, because we don't have so much time, by working against an abstract monoid. So it's a monoid. Well, there's a description here. It's a set together with a binary operation on it, which has a unit and satisfying the axiom of associativity. So if we want to program against all monoids in general, we can just define this thing as a record. And because class types are first class in ACTA, we can just say my monoid has a carrier and it's a set. So a monoid is a set together with a binary operation on it. So I have a binary operation which I'm going to call something like this, which might remind you of a Haskell thing. It's a binary operation, so it's taking two arguments and returning a third and returning a value. It has a unit, so I'll call it empty, I guess, to stick with the Haskell idea. And then there's a bit of characterization, so it satisfies the axiom of associativity. So if we want, we can say, okay, we have a type and operations, but it's not just like in Haskell where you're just saying, I have these operations over that type. You're also saying, oh, by the way, they respect some equations. And so now, because you're able to enforce the equations statically, you will also be able to prove that operations over an arbitrary monoid actually have good properties. And their properties. And so we have ASOC, which is saying that X, Y, Z, oh yeah, it's a bunch of fields where you have X, Y, Z. So the brackets are not needed, is equal to X, Y, Z. I'm just going to write it first, and then sprinkle some brackets here and there. So let's say to the left here, and here we'll do it to the right. I will need to import equality. Positional equality using whoop, whoop, whoop. One too many. Oh, okay. And we're almost there. The only tricky thing here is that in this mathematical description, we said it has a unit, but a unit is not just any value, right? It's a value that behaves well with respect to the binary operation. So we are just missing that one or two, actually, laws saying that no matter what you have, if you combine it with the units, you just have the same thing over again. So the unit doesn't do anything, a bit like 1 for multiplication. And then we also have it on the other sides. So why do we need to specify that it's a unit on both sides? Well, you'll notice that we say that the binary operation is associative, but we didn't say that it was commutative. And so as a consequence, if you know that something is a unit on the left side, you cannot prove that it's also a unit on the right side, because you can't just swap the two values around. So you need a bit more like base assumptions, because you don't have this very powerful commutativity principle. But oh, okay, well, I could throw it in. A lot of the operations we know and like satisfy commutativity, which is saying that it doesn't matter whether you combine x and y or y and x. So for plus, it's true. For minus, not so much, right? 3 minus 1 is not the same as 1 minus 3. So in this case, we are not going to assume it. Well, minus is not associative either, so it wouldn't be a good example here. But we're not going to assume commutativity, which means we'll be able to capture more examples, but we won't be able to rely on this extra assumptions. So there's always a balance to strike when you're modelizing something between assuming as much as possible so that you have really powerful reasoning principles, but also minimizing the number of assumptions so that you can use your results as much as possible in cases where maybe the extra assumptions are not true.
Plus is only commutative because numbers are boring.
Yes. Well, do you want to give us your favorite example of a monoid, Connor?
Well, yeah.
Maybe you don't have a favorite.
I do have a favorite.
Oh, okay.
I mean, it depends on whether it's the weekend or not. But right. You're going to tell me I should import a list library.
If you want to redefine everything by hand.
I might have to do that. Also, we'll see how your keyboard goes. But, so, we should probably replace this definition of lists with the library one, but this way I get to type in ASCII. Yeah. Okay. Right, so that's lists, and I'm going to define an operation that we know and love. Fingers. Right, so you see, I'm lining up that we're going to get one of the monoid laws for free, but we'll have to work on the other two. Okay, so we've got lists, we've got a binary operation, which is just concatenation, and this is, right, this sort of echoes the experience of monoids that you have in your life. Right, your most basic monoid that you encounter in the real world is a shelf. Right, you put stuff beside each other on a shelf. You can have nothing on a shelf, you can have one thing on a shelf, you can have multiple things on a shelf beside each other, and the only brackets are the ones holding the shelf up. One thing that's nice here is that list is a way to extract, to turn any set into a monoid. So what would we want to say? List monoid. I don't know how you want the capitalization conventions. Should probably have a capital. Bad news. I see. No, fingers are behaving extremely badly. Right. Have we seen copatterns?
I don't think we have, no, but maybe we could.
All right. There are various, we're trying, so monoid's a record type, and there are various things we might do to build a record. I might do this, and then it gives me a a load of fields to fill in. But
So that's using refine, right? Control C,
yes.
Control R.
But there's another thing that we can do, which has the key advantage that it keeps us working left of the equal sign. So you know that when you're programming with a data type, you can do a thing which says split this variable into cases. So when you have data as an input, you can split stuff into cases. Well, the same is true when you have a record as an output. You can say, split this problem into pieces. You see, it says a very small print, pattern variables to case, parentheses, empty for split on result. So that's what I'm going to do. And then it's going to give me a bunch of stuff. Should I open Monoid? Okay. So, because I haven't brought the field names into scope, which I'm now doing, it gives me lots of stuff. Right. That's nicer. So it's saying, okay, what are all the projections from this thing? But the good news is that I'm still on the left-hand side. I can still do left-hand side stuff, and we'll see that in a moment. So let's say, what's the carrier of my monoid? That is list X. And then here, I can say, well, this thing wants some inputs. Okay. And what's the neutral thing? It's nil. And now I have to prove associativity. You see my goal talks about 3 lists. Shall we make the... How do I make the font bigger?
Control scroll into it.
Control.
And you scroll into it.
Ooh, I'm in the wrong place. I want to be in the mini buffer. Oh, no. I just want the mini buffer to be,
Yeah.
or the AGDA information buffer to be more legible.
Oh, that's it, I guess.
Right. So we're back here. Font is now enormous, but that's all right. So goal 0 is saying you've got 3 lists, you've got to prove this thing is associative. And this is, so if I reload, I now got my 3 inputs on the left. And I'm free to do things like case analysis, right? We haven't lost the ability to do all of those lovely left programming things. So deciding to split a problem to build a record into multiple problems to build the individual fields is a very useful left programming move, and almost no programming languages support it. AGDA does it. Okay, so it's absolute textbook, why is it stuck? And we know that the append is strict in its first input, so we should really look at x's here. Both sides of the equation, if we normalize.
Before you do that, Connor, let me point something out. If you look at the goal 0, then it looks really horrible, right? Because it looks like it's talking about appending list monad x with something else.
Yeah.
So this is what happens when you use an infix operator as the name of a field in your record. And the way to get out of it is usually to try to normalize as much as possible, right? Because that's going to compute that operation into the actual operation concretely here, and then it looks sensible again, right?
Right. So we can see left-hand side and right-hand side are both stuck because we don't know what x's happens to be. So that's the right thing to split on. And then hopefully that one's just straightforwardly true. And this one, you're going to tell me I also need to import Kong from some library. Should that just be in the same import as we had at the top? So what's the syntax? Semicolon Kong?
Yes.
Like that, except with only one N?
Yeah.
Excellent. So this is Kong x comma minus underscore query. You see we are now reduced to the induction hypothesis. Have they fixed it so that I can do that? No, they haven't. So what do I want to do? Swear. What's happened to the... I've just done some... I'm in scroll lock. How do I get out of scroll lock?
I think you click on scroll lock.
I hate computers. Let's see if I'm lucky. Right, we managed to finish that proof. That's only 2 to go. And right, so let's see. Goal number 1, I suspect, is going to be the easy one. Yep. You can see that one is already computed away because the nil was on the left. So we just got that from the definition. This one will also require some work. Right, this is a classic example of like under-ambition. The only thing Agda knows about append is the equations we use to define it. And the fact of the matter is that here we are talking about algebraic properties of append, and Agda has no interest whatsoever in doing algebra, which is really annoying, frankly. Essentially, Agda persists as in the tradition of the last half a century of turning up to an algebra fight armed only with arithmetic. And it's really not good enough. And here it's going to be another job for Kong. And then I'll see if I can do this less violently. This, well, Control W will do the right thing. You know the old ways. Right. So we've managed to show that lists are a monoid. It's like putting things next to each other. It's clearly associative. And you can also see that if there are any interesting elements, right? You know, if you can tell the elements of a list apart, then you have no chance of it being commutative. Whereas if you instantiate the unit, this element type X to be the unit type, only under those circumstances do you get something that's commutative. That's what I mean by saying numbers are boring, right? Numbers are what you get when you say lists with elements you can't tell apart. That's what a number is. It's a list. It's a list whose element type is boring. Okay, So I don't know where you want to go next, but
Well, yeah, so I wanted to say a little something about how these work. So you have to be a bit careful, and actually someone I think in the lab last week was showing me a hurdle they were encountering with something like this. So here, if you look at these definitions, we're doing pattern matching and so on, and then there's computation in the types happening, but the computation is only through this append, which has been already defined somewhere outside of the block. And so Agda has already checked that append is safe, and it can run it, it can do all at once with it, that's fine. But if we had defined append inline here, then I think Agda gets a bit scared about evaluating it, because if you think about what this is doing, right, you're defining an entire record, and then locally you're recursing to describe one of the fields. But if a further field needs that computation to also happen, that further field is also talking about the record, which you're currently defining. So then are you relying on evaluating something you're currently defining, which is maybe not yet well defined? It's kind of hard to see. I mean, you could try to do the dependency graph and so on to make sure that the recursive definition of append is like really isolated, but Agda doesn't bother doing that. It just says, I don't know. In the goals though, it will show you the reduced versions of things, because morally the goals exist sort of in the ether around this definition, and so everything that's in this definition is checked, and then when you're looking at the goals, we know that so far this definition is safe, so it's willing to reduce it. So then you have this very counterintuitive thing where you can see the computation happening in the goal, but as soon as you put the proof in, it refuses to type check because you don't have enough reductions happening. So for the proofs, it's fine, you can do it, just do the local pattern matching and so on. When you're defining the operations that are actually showing up in the types of the proofs later on, it's better to lift them to the top level just to be on the safe side.
For readability as much as anything else. But
yeah, that's
you're basically, you know, Agda is not going to work overly hard to analyze the kind of tightly coiled spiral of data dependencies that you have when you build a record of all of the things. So what we're really doing is just pointing out that there is no data dependency.
I mean, it could. The problem is that this is a feature that was added later on, well after termination checking was introduced. And then there's the question of shipping your feature versus adding support for every aspect of the language. So sometimes you have to make some compromises, right, to at least get the projections working. Right, so once we have our definition of monoids, and we have at least one monoid, because sometimes you define an interface, and turns out what you're expecting of your carrier is a bit too strong, and you cannot build any example of such an interface. So it's always good to check that there's at least a good one. So once you have this, and you'll maybe recognize this pattern from the coursework if you've already looked at it, you can define a module which is parametrized by one such thing. So you're just saying, I want a monoid, any monoid whatsoever, and all of the things in the indented block below the module keyword will be relative to that monoid. Yeah. So the first thing to do, of course, is to open it.
You could, of course, now move the open import data.list.base to the top of the file and get rid of.
We can reuse your lists. That's fine. We have all the bits, I think. Right, so when we open this, you can see that we're using the record as a module. You can always do that. And if you pass an actual value of the record type, it will actually partially apply everything and just give you the operations. And because carrier is long to write, I decided to rename it to M. And as we said in the definition of monoids, so we have a binary operation and brackets are not needed. So if you have a list of values in that monoid, no matter how you combine them, the results will be equal, as long as you're not using commutativity.
Yeah. there's a
It's,
thing here. Monoid structure enables you to combine any number of things into one thing, remembering that there are some important numbers, like 0. So you have to be able to get a thing out of nothing. And then if you've got one thing, you combine it to make itself. And if you've got more than one thing, then you need a way to combine 2 of them, so you have fewer and fewer things until you've got one left.
But luckily, you have a binary operation, so.
But we're now going to...
Okay, so we can introduce the list, look at it. The names are disgusting. So if we have no element to combine, as Connor was saying, we can just use mempty. Whoop. No. So I'm going to show you a bit of scope management magic. So if you want to do something locally that should be undone on the way out, you can just define an anonymous module. So I'm going to open Monoid, but only locally to this thing. And then if I move this thing to the right, Monoid should be open for this definition, and then we go back to the top level, so it's closed again. And now my definition should work if I use mempty. Yeah,
Cool.
it works. And it's not just for, so Monoid, as I told you, right, it's morely defining a record. When you're defining a record, you're also defining a module that contains all of the projections from the record. But this is not limited to just modules that are induced by a record. You could import anything you wanted here locally, and then it goes out of scope again when you go back to the top level, so that you're not polluting your scope with unrelated contents.
Is it maybe worth saying what the problem was? So we opened Monoid twice, right? Once in general up there, just saying we have access to all the fields, and then here we're opening it, instantiating it to this particular Monoid. But that means that when we say mempty, we don't know if we mean the mempty for this Monoid or the general mempty that was open up there, right? So we said that's why we got an error message, and that's why we moved the one further up out of scope again, so that there's no conflict here.
Okay, so in the base case, there's nothing. Then Connor said, if there's a single value, we can just return it. But I'm not going to do this special case, because if you remember the rules for mempty, you can tack on mempty at the end or at the beginning, it doesn't matter. So if you have a single value and you return it immediately, like here, it's the same as returning it, but combining it with the mempty that you get for the empty list. So the more general pattern is to say just, I have the X, and I'm going to combine it with, well, I could try X's, but it's the wrong type, because it's a list, but we're looking for an M. And of course, here we just squish recursively to combine all of the values. And if you squint hard enough, you might notice that this is a pattern that you saw in 3.1.6, maybe in 2.6.0 even. And I guess I can just redefine it here. The dreaded folder, which was telling you that if you know how to merge an X and a Y to obtain a new Y, and
could you indulge me by writing the arguments of fold R in the wrong order?
Which wrong order?
I want this function here, and then I want the list of X's next.
Oh, I see.
Because I've got another favorite monoid.
Okay. Yep. So if you know how to merge X's into an existing Y to obtain a bigger Y or like a compound Y, and you have a base Y you can start from, then you can squish a list of X's into a single y. So if we remember, of course, this is just muscle memory, not the implementation. Oh, maybe not. The implementation of this thing. It should be something like this. So if the list is empty, you just return the base value that you had. And if the list is non-empty, then you combine the x that you have using this merging function with the result of squishing the rest of the list into a y.
Now
With the original base. With the original base case. All right, so I have this thing. And you can see that n here is just returned immediately, and here it's at the end. So if we have a bit of magic, aka function base, we can import the identity and composition. So I'm using the ticked composition because this type is not dependent. And if I'm using the full-blown composition, it might be a bit hard for that to figure out all of the implicit arguments. But if I'm using the ticked one, the tick is saying it's a boring one. And so it will know that there are no dependencies, and so that the problem is easy, and I have more solutions automatically. It's a purely technical detail. So n is turned into n, that's just the identity, and n is turned into cx of blah, blah, blah. It's the composition of cx, blah, blah, blah.
It's almost as if functions that go from a type to itself, right? There's one that does nothing, and there's a way of squishing two of them together. In fact, this thing all along that you've been using forever is really telling you about an important relationship between two monoids.
Yeah, and let's just make it explicit, right? So this is another set to monoid. I'm going to use the record constructors this time because I think it's a fairly simple one. I don't need to do pattern matching.
Cool.
Ugh. All right, let's do this thing. I don't know how to do it multiple times.
Aha. Jacques taught me a trick for doing this rather neatly.
Oh, there's also a line regex equal. Well, okay. Not quite. Let's just be happy with this current indentation. So what Connor is saying is that, so I called it endo because so you have functions which are between two arbitrary sets, and then endo just means inside, right? So endo functions are starting from a set and going back to it. And lots of interesting functions are doing that. Of course, it's a strong restriction, right? You can't just have arbitrary functions. But then we're looking at this thing. Okay, this could be a lot of things. We could return the first one. We could return the second one. We could apply them in a row to this value. We could apply them backwards. The sensible thing to do, I guess, is to use composition. I suppose you could do reverse composition. Do all of these work, actually?
Yeah, I mean...
not the constant ones, but...
Yeah. I mean, so monoids are, of course, a massive buy one, get one free operation.
Well, that's a good one, yeah. So just like we were saying in the folder, so when you're not doing anything, you're just using the identity. When you're combining two things, you're using composition. So we've already used the pens. Now we can use the identity for the mempty. And if I normalize this enough, because of the way function composition works, it works just by plugging things together, right? It doesn't actually pattern match or anything. It can compute readily. And then if we look at it hard enough, we can see that x, y, z, like the things are in the same order. So it should just be true on the nose. Let's see. I don't care about the names of these things. And now we have a function composed with the identity is equal to the function. Well, if I normalize this, okay, there's a bit more magic actually that I didn't mention in the other case, but it's going to be more visible here. So Agda is saying, oh, so we had x composed with identity, but identity only compute if it's applied to a value. Luckily, Agda can sort of knows internally that any function is equivalent to a local, like anonymous function, which takes its argument and then passes it to the function. So f is equal to lambda x, f of x. That's internally known. And so then from that, we get that the composition can compute, then identity is actually applied to value, it reduces. All of this to say that this equality is again trivially understood as valid by ACTA. And here's just the other way around. We turn this into lambda a identity composed with x applied to a, which reduces to identity of x of a, which reduces to x of a, and then we have lambda a x of a equals x. Whoop. Right, so I wanted to, going back to this thing, redefine now the arguments of folder are in a weird order for me. Folder. Empty. Oh. Oops. Okay. So in the base case, we're doing nothing. In the cons case, we're just using append to tack on the x in front of the result of the recursive call. So we can refactor it as this. And then maybe Fred can prove that it's compatible with ++.
Yeah, let's see what happens. Can you change the keyboard?
Ooh, sorry.
Meanwhile, we can think about this. So what would it mean to squish together a concatenation of two lists, right? So what squish is doing is it's just taking all of the arguments in its input lists and kind of using the operation on them one after another, right? So if we are squishing x's and then y's, you'd hope that this would be the same thing as squishing x's and squishing y's and then combining them in the middle, right? So something like squish x's and then append squish y's. That's the type check. So that's something in the monoid, and the thing on the right here should be something in the monoid. Of course, there's many things I could put here. I could claim that it's empty. That would not be true, but the fact that it type checks is not a very strong guarantee here, right? But I could believe this because, as Guillaume was saying, it doesn't really matter how we split up our input list into two pieces. We're just going to go left to right and combine things, right? So let's see if we can prove it. I'm not sure why these things are implicit. I need to make them explicit. Okay. So now, because Guillaume tried to be clever and use this fold R operation, our goal looks a bit scary, right? But we can think back to how was fold R defined. It was doing pattern matching on its list, right? So we play the usual game of why is it stuck? Well, this fold R is stuck because we don't know what this list is. And this list is stuck because we don't know what access is, right? And this folder is stuck because we don't know what access is. And this one is stuck because we don't know what wise is, I suppose. But if we look at access first, I think that's a good move. Pattern match and access. Then we see what that does for us. Okay. So our left-hand side is simplified. Our first part and right-hand side are simplified a lot. This hasn't changed because it had nothing to do with access. But now we see that what we're asked to prove is that mempty combined with something is then something, right? So is this mempty this way around? Yes. Okay, so it takes the x. My x is this whole thing. Okay, and then I just need to flip this equality around, right, with a sim. Okay. Okay. What's happening here? Okay, so let's look at this. So on the left-hand side, we have an x followed by this fold R. And on the right-hand side, we have an x followed by this, followed by that. But by the induction hypothesis, this fold R of this concatenation should be the same thing as this followed by that, right? So let's see what we get if we do a recursive call. I guess I'm going to try to do a rewrite. Okay, so we have replaced that fold R of a concatenation with the operation applied to the pieces. And it looks quite promising, right? We have the same thing in the right order, first x, then squishing x's, and then squishing y's. It's just that the brackets are wrong, right? But one of the laws we had in M was exactly that we can put the brackets however we want, right? So if I use associativity, like this, okay, and then I know my first thing is x. And I know that my last two things are complicated to type, so I'm going to try to just use underscores for them. Give that. And then I see that again, I want this equality to be flipped, right? So here I have x on its own, and that's what I have here on the left. So I'll do a sim on this. And I got away with the underscores. So I was able to fill in what these things were supposed to be. If I'm bothered by it, I could go back and I could solve for these. Just for documentation to see what it is.
Which you could turn into squish axes.
Yes.
Ah, okay, fine. So, right, so this is actually squish wise, right?
Yeah, much nicer.
Okay, that's a bit tidier indeed. Okay, so what did we use? We used that we had a unit on one side, and we used associativity. But we didn't use the unit on the other side, right? Because our fold R is really biased towards putting things on one side. So that's where the unit is going to end up eventually. Right?
It's funny you should say that because Yeah, so if you remember 316 again, oh, did I? No. We saw, so you have this folder operation which turns, let's say, 1, 2, 3, 4, empty, into 1, whatever notion of combination you're using, poop. But the point is that these are bracketed this way. Right? Oh, I guess. Well, where was I? 1. I guess here it's better to use this thing. This way they have the same size. So looking at the lists, they are morally parenthesized to the right. And this thing is just replacing all of the conses with the combination operation. And then mempty is a terrible name because it's very long. But you get the idea. But we also saw a different operation, which is taking your list here and instead computing, well, something like this. Mempty combined with 1. And then to the left, combined with 2, okay. Combined with 3, combined with 4. Whoop. Now I don't know how many I need. Yeah, this is it. Maybe enough indentation will save me. Yeah, it's aligned again. So we had this fold R operation, which was giving us this thing by replacing all of the conses with whatever function it was passed, and then the base, like the empty list, with the base case. But we also saw fold L, which is starting from a base case and then accumulating the values into it. And because we said that brackets do not matter, it shouldn't matter whether we are computing fold R or fold L. So let's go and define fold L. Fold L is here. So it's starting from the base case. If I can stop jumping around. Oh, I didn't rename it. It's starting from the base case, so from the y, and then it's absorbing a new value x into the y. Should I keep it like that? Maybe I should keep it like that, whatever. So we have the c, well, I guess I should put the initial value to the left because it's coming first, morally. So this is m, c, x's. And then matching on x's, if there's nothing left to do, well, I can return the result stored in the accumulator, which is actually a better name for this parameter, because as we'll see in the next case, we just shove more values into the accumulator as we go along. And that doesn't type check for some reason.
Still need to give the C.
Yeah, I'm missing the C. So if you remember the small diagram, right, the accumulator is sort of on the left. It's what we have computed so far. So this thing. So far we've computed mempty combined with 1, then mempty combined with 2, with 3. As we go along, we shove more and more information into the accumulator. So when we encounter a new value, we just combine it with the accumulator, and we keep processing the rest of the list. And one really nice thing to notice between these two definitions, right, is that this one will compute the rest, the result on the rest of the list, and then eventually come back and combine it with the value it found at the head, right? So optimizations can change that and so on, but if you think about it naively, every time you encounter a value in the list, you're going to push something on the stack, remembering that you will need to do C of x to whatever comes back out of this evaluation. So the stack is going to grow linearly with the input list. Whereas here, what you're seeing is that you're defining fold L directly in terms of fold L. So you don't need to push anything. Whatever value comes out of this thing will be returned immediately. So this, provided that this doesn't grow, etc., could be constant space. So it might be good in some cases to use fold L instead of fold R. And the nice story, and I don't think we'll have time to do it, but it's a good thing to try to think about, is that you could define squish prime list m to m in terms of fold L. So if I remember, I had the accumulator as the first thing, so it's empty at the start, and then I need a way to combine the values. So that's this thing, and then you could say for a monoid, I should make it explicit, it doesn't actually matter which one you use. So this is doing it right to left, this is doing it left to right, but because we said the brackets don't matter, you can actually process your list in whatever order you want. And even better than that, the theorem that Fred proved tells you that you don't even need to respect the linear structure of the list. You can transform it into a tree, right? This is just a branch with two sub-lists at the moment, but you can think that you could apply the same processes to these two values. You can actually transform it into a tree and then process the subtrees in parallel. So by having this constraint that whatever you take as an argument is a monoid, you're actually able to completely restructure your computation so that you can perform it in a different manner, but still obtain the same result. And the in a different manner is hopefully giving you something more performance. So if you want to think a little bit about how to prove this, it's a nice challenge, and otherwise I think we'll see it tomorrow. Oh, I should stop the